Okay, here we go again, I heard. That's it. Here we go again. Okay, we're here talking about the solubility product. Well, we discussed now the solubility product of the AB type. There were some questions about the AB2 type. Let's come back to the AB2 type. We had that, if you remember, when we talked about the ionic bonding. The ionic bonding, we have it in salts, and there are some of the AB2 type. Here, when we solve it, we have a cation 2 times positive charged plus 2 anions 1 time negative charged. And the example was calcium chloride, for example. If we solve it, we have calcium 2 plus 2 Cl minus. The ionic product of this calcium chloride is now the concentration of the calcium 2 plus ions times the concentration of the Cl minus ions squared. We even had another example, the A2B3 type. Now we have 2A3 plus cations plus 3B2 minus ions. 2 times 3 plus is plus 6. 3 times 2 minus is minus 6. That's fine. The solubility product of the A2B3 type is the A3 plus ions square times B2 minus ions cubic. The concentrate or the unit is now mole to the power of 5 over liter to the power of 5. Here the unit is mole to the power of 3 over liter to the power of 3. An example of an A2B3 type, do you know one? Oh, Fe2O3, for example. Here, this is the ion plus 3 and the oxygen minus 2. Oh, could be an example of an A2B3 type. And as already mentioned before the break, oversaturated means more than the component in the solvent than soluble at the defined temperature. If we have it solved at a high temperature and we cool it down. In this intermediate phase, when it is cooling, it could be solved more than normal possible, but after a while it will precipitate. Precipitation means we form the solid crystals again. Oversaturated. it is more solved than normally soluble in the solvent at the defined temperature. It could be created while heating up, solving more, and cooling down. So creation of an oversaturated solution, for example, by heating up the solution, means solving more at a high temperature, cooling down again, and then for a moment we have an oversaturated solution. When it's cooling down further, we have the precipitation. That means forming of the solid form of the component again, which can be filtrated or lies on the bottom, whatever. So that's about solubility and solubility product. Now let's switch to a new subchapter. We are all in the chemical reaction, fourth main chapter. 4.7 now is acid-base reactions. Let's first talk about acids and bases or alkali. Well, The most famous acid is hydrochloric acid. I think everyone knows. If we add water or we solve it in water in H2O, we form H plus ions and Cl minus ions. It could be written even as H3O plus plus Cl minus. Here we just add the water to the H plus, then we have the H3O plus. Another one is the hydrosulfuric acid or the sulfuric acid, H2SO4, right? Here is another acid. We call it a 2-protonic acid. This is a 1-protonic. We just have one proton, which could be spent. Here we have two of them, H2. So this one is in a first step producing H plus in water plus hydrosulfuric anion. And this one additionally can spend a proton, and we have the sulfate 2 minus anion. So 2 steps where protons can be delivered to a partner. Of course, the acidic character of the first step is bigger than the second one. Because here, the first proton is delivered more easy than the second one. So the acidic character of the first step is bigger as the acidic character of the second step. Those two are mineral acids. We even know organic acids. Do you know one? Vinegar or acetic acid. Do you know the formula? Or someone? Yeah. And when we try to do it more structure, to draw the structure, it is CH3 COOH. Oh, that's acetic acid. And this one is an organic acid. It's an example. And organic acids always have these part, COOH. That is the character of a carbonic acid or organic acid. COOH. Here we have a 1 sigma and a pi bond. So the carbon, what's the hybridization of this carbon at the acidic part here? What's the hybridization? sp3 is that one. What is the sp3? It always means 4 different partners. It means tetrahedral surrounding. In the middle of the tetrahedron is the carbon. In the edge is HHH and the COOH. And now here we have a pi bond. It's sp2. It's trigonal planar. The surrounding is trigonal planar. Please keep that in mind. We discussed a lot about that at the beginning of a few weeks ago. That's an sp2 carbon, and that's an sp3 carbon. Okay? That is what you should be able to describe. And here, what carbon can be spent? It's this one. That is the carbon which can be spent. I'm missing my red color today. So when we look to this acid, we have an H plus, and this is that one, plus. Now I short it a little bit, CH3, CO, O, and now when we have to draw the structure, we have the negative charge at that carbon, minus. Because the H plus is spent without an electron. This electron remains here on the oxygen. Normally we need 6. It's in the 6th column of the periodic table. We have 1, 2, 3, 4, 5, 6, 7. So 1 negative charge remains here. What do you know about a structure like that? Is it stable? Why not? We talked about this in a similar structure in the CO3 2 minus. This one can be in a mesomeric structure written like that. See, now the electron pair comes over here, and this one comes over here. So we have a second option. Now the negative charge is on the upper oxygen atom, and the double bond is here. Oh, that is the second option to draw is an ion, and it's stabilized because the electron pair can move in between those two. It is not similar to the aromatic character where it can be in a cycle rotating, but it can move, and that always means it's stable. It is more stable compared to just having one option. And we talked about that mesomery. We did it on the example of CO3, if you remember. The carbonate anion, we have 2 minus. And here we have even more options. It can be jumping over here, and then you have the negative part here, the double bond here, and it can be even come here. So the negative charge can be delocalized over all 3 oxygen atoms. The CO3 2 minus. Mesomery. Mesomery. Please check that once more in your notes. And here, for the organic acid, we just have 2 options, but it helps to stabilize these anions. What do you think when we draw the acetic acid molecule once more? CH3, CO, and O, and H. This is how it is bonded. What do you think about the the location of the electron pair here, is it more on the hydrogen or more on the oxygen? Why? The electronegativity is big compared to the hydrogen, so it is more on the side of the oxygen. So even in the acetic acid as the molecule, it is already more on the side of the oxygen. And now it is spent totally to the oxygen, the electron pair, and the proton is split it off. So we have a quite high acidic character. What does it mean? An acid is defined as a proton donor. Meaning a proton is spent. Proton is a H plus cation. That is an acid. And this is an organic acid, and the other one were mineral acids. Hydrochloric, sulfuric, phosphoric acid. When we talk about an alkali, well known is the sodium hydroxide. In water, we have the formation of sodium plus ions and the hydroxide anion, OH minus. Another one can be the barium hydroxide. Now we need two OH because barium, if you look to the periodic table, is in the second column. The second group has two electrons which can be spent. And therefore, we need two negative charges. So we have the barium 2 plus 2 OH minus. In general, an alkali is a donor of hydroxide anions. The OH minus. So an acid is a proton donor, and an alkali is a hydroxide ion donor. When we now combine an acid and an alkali, how do we call these type of reaction? An acid and an alkali we put together, give salt and water, and we call it neutralization. So, for example, we have a strong acid, hydrochloric acid, H plus Cl minus in water, and we have a strong alkali, sodium hydroxide. And you're right, when we add it, we have the Na plus ions and the Cl minus. So that is in solution solved common salt plus H2O. Now that is a strong acid. And that is a strong alkali. What are you expecting will be the pH when we add them 1 to 1 after the reaction, the pH of the solution, 7 will be 7, yes. So here, the pH at the end will be 7 after the neutralization. So in general, an acid and an alkali forms a salt and water. Acid plus alkali forms salt plus water. And that's a general rule, and the reaction is called neutralization. Coming back to the hydrochloric acid, HCl, that is the acid. And now we add water, or we put it into water, into H2O. Then we have the H3O plus. Plus the Cl minus. Or when we leave the water away, H plus and Cl minus. This is the acid, and this is what we call the conjugate alkali. So there is always an acid alkali pair. Because when we read it from the right to the left, it acts like an alkali. It is accepting the proton. When you read it from the left to the right, it is an acid. It's delivering a proton. So the Cl minus here is the conjugate alkali. Or in a more general way, we have the HCl and we have H2O forming now H3O plus plus Cl minus. This is now what we already did, I think, last week once in an example. That's the acid 1. And that is the conjugate alkali 1. Alkali 1. And this one is now the alkali 2, or here, let's say that is the acid 2. And therefore we have the conjugate alkali 2. So here, this is the acid alkali pair, and vice versa, the acid alkali pair. And we already talked about the amphoteric character of water. H2O can do both. Then we have here acting as an alkali or as an alkali, a proton donor. Then this is the conjugate acid. And when this one acts as an acid, then this is the conjugate alkyl. Alkali is accepting a proton, and the acid is delivering a proton. The alkali is accepting a proton, the acid is delivering. The alkali even can be described as acceptor of protons instead of donor of hydroxide ions. And that is what we call the autoprotolysis of water. So water has an amphoteric character. Meaning it can act as an alkali or as an acid. Amphoteric, amphoteric, A-M-P-H-O-T-E-R-I-C. That means it can act as an acid or an alkali. Maybe there is another H. If this is possible, we call it amphoteric. The water has an amphoteric character. It can act as an acid or an alkali. Well, normally we have H2O and we have H plus OH minus. And we know it is normally more or less totally, or not totally, but mostly on the left. The concentration of this H plus ions is 10 to the power of minus 7 mole per liter in a neutral solution, and even the concentration of OH minus is 10 to the power of minus 7 mole per liter in a neutral solution. So that means the concentration of H plus in a neutral solution is similar to the concentration of OH minus, and this goes 10 to the power of minus 7 liter. What is the ion product? L from water is, what is it? It is the concentration of H plus times the concentration of OH minus. It's 10 to the power of minus 40, now mole square over liter square. And we already talked about the pH is defined as the negative logarithm to the base of 10 of the H plus ions, the concentration of the H plus ions. And in a neutral solution, it is 7. Because here negative logarithm to the base of 10 is 7. The POH is defined as the negative logarithm to the base of 10 of the OH minus ions. It's 7 either, because here 7, it's the same. And this means now pH plus POH is 14. Please be aware of these definitions. That is important. In pure water, we know the concentration of the water molecules. The concentration just now of the water molecules is 55.5 mole per liter. That is the concentration of water in water. How many molecules do we have in 1 liter of water? It's 55.5 mole. And when we now use the law of mass action, for the water, we have here H2O plus H2O, mostly on the left side, H3O plus plus OH minus. Just repeating. Now, the law of mass action means we calculate the Kc is, when you remember, what do we have to calculate when we use Kc for this reaction? H3O plus times OH minus concentration over, not 2 times, the concentration square. Yeah, that's the difference. Square. But now knowing that in pure water, the concentration of water is fixed. And this is very high compared to the concentration of the H3O plus or OH minus. So we can integrate it to the Kc. If we write Kc times the concentration of water square is the ionic product of H3O plus times OH minus. It's the same. Leave it. And now we say this is what we call Kw, the ionic product of water, where already the concentration of the water molecules is integrated because it's fixed square. And that is what we know is 10 to the power of minus 14 mole square over liter square. And this is constant. The Kw is 10 to the power of minus 14. And that is what we already know. It's just in different ways of explaining, meaning the concentration of H3O plus is similar to the concentration of OH minus in a neutral solution. If we add an acid, we decrease automatically the OH minus, because the product of both is always 10 to the power of minus 40. No, for example, we have now, just an example, adding HCl to water, leading to that we now have a concentration, for example, of the H3O plus is equal to H plus is, let's say, 10 to the power of minus 2 mole over liter. We added H plus via adding hydrochloric acid. What does it mean in this example for the concentration of OH minus? In this example, it must be 10 to the power negative 12 mole over liter. The pH is, what is the pH? This here, pH is 2. And the pOH is 12. Oh, I forgot the O. OH. Thank you. Well, we already started, I think, a little to discuss about the strength of acids last week. Let's repeat it. Strengths of acids. So we have an example 1. We have an acid HA, for example, hydrochloric acid. And we put it in water. Then we have the equilibrium, knowing not exactly is it strong or not at that moment, H3O plus and A minus. When we use the law of mass action, Ka, it is now, we don't have to calculate the water. It's always the 55.5 mole over liter. So don't care about it. We have the H3O plus concentration times the A minus concentration over, of course, the concentration of the acid we have to calculate it. Now we use another parameter, we call it pKa. What do you think is the pKa? No, not pressure. We come to pH, pOH, and now pKa. It's related to the strength of an acid, but the definition mathematically, the mathematical definition is similar to pH. Minus log to the base of 10 of Ka. Now, let's say we have a strong acid. So the equilibrium 1 is mostly on the right side. Because it's a strong acid, it is mostly on the right side. What does it mean for Ka when it is mostly on the right side? Ka is big. That means Ka is high, big. But what does it mean for pKa? When you look to the definition, sorry, is it high or low? When the Ka is very big, now we have the negative log of the K. It must be low because we have the negative log of it. So a low pKa means we have a strong acid. And sometimes we find in the literature the Ka, but very often we find the pKa levels. Then we have to think about what does it mean. Ka high, strong acid, but for pKa low, strong acid. And that is what you should think about, because you can look it up in tables, what is the strength of different acids, and you will get Ka or pKa. Time to time, maybe even both. But then you have to evaluate, is it strong or not? So the pKa value defines the acidity of an acid. Vice versa, the pKb level or value defines the alkalinity of a alkali. Alkali, sometimes we call it base. To give you an example, pKa of HCl is -8. And the pKa of acetic acid is 4.74. Now you have to decide which one is the strong acid and which one is the not as strong acid, the stronger one. pKa is low, -8, compared to plus 4.7. Or, of course, the HCl is much stronger as the acetic acid. This is strong acid. And this is a weak acid. again, let's come back to the weak acid here. It is a little bit more difficult to calculate the pH level of a weak acid. A strong acid, it's not problematic because for the strong acid, we say it is totally on the right. Then we say the concentration of the H3O plus is similar to the concentration of the strong acid because it's totally on the right. And then when we know the concentration of the acid, for example, 10 to the power of -2 mole per liter, what will be the pH of that strong acid? Again, the pH, 2. Yeah, the pH is 2. So for that, it's easy. We just can say it. When we know the concentration of the strong acid, which is totally has totally provided all of the protons to the water, it is the concentration of the acid similar to the concentration of the H3O plus. So in the example, 10 to the power of -2 mole per liter, the pH is 2. For a weak acid, we can't say that because it's not totally on the right. It's something in between, and we are not sure about it. So it's a little bit more difficult to calculate the pH of a weak acid. And that's what we'd like to do in the next step. So we use the acetic acid as an example. And we already know the formula CH3 COOH. Now, this is the formula of the acetic acid in water, H2O. We are not sure about, but we know it is a weak acid. It will be more on the left side. And we will have the CH3 COO minus plus H3O plus. We can even write it short, which we say that is the acetic acid, acetic anion. H-ats is the acetic acid plus water. And we know it is not very strong. And then we have the acetic anion plus H3O plus. This is now our example 2. In short, to have less efforts to write the chemical structure above, but in short here. Now, what does it mean for Ka? Please help me. When we write Ka related to the law of mass action, what do we have to calculate? It is the concentration of the products. It's Ats minus times H3O plus concentration over water. We do not have to calculate. It's fixed concentration, 55.5 mole per liter. It's integrated. So only the concentration of the acetic acid, H-ats, is relevant. And we just have one. So no square or anything else. And we know the value of that is 1.8 times 10 to the power of -5. Now, what's the unit? Mole square over liter square divided by mole over liter, so mole over liter remaining. When we now look to this equation at 2, when we look to it, what does it mean? When it is spending a proton, in the case of, then we have a 1-to-1 ratio of ATS minus and H3O plus. So we can simplify and say, in this case, the H3O plus concentration is the same as the ATS minus concentration. Because when we look to the chemical equation, it's 1-to-1. If this is 1-to-2, of course, then it's not the same. But here it is. When we know that, we can or integrate it into Ka, and now say, okay, Ka, ATS minus is same as H3O plus. So it is H3O plus concentration square over the concentration of the acetic acid HATS. It looks like now a little bit more clear. Now, when we try to have a look to the H3O plus concentration, we say H3O plus square is now Ka times the concentration of HATS. It's just mathematical transforming this to that. Well, okay, that means now the H3O plus concentration is the square root out of the product Ka times HATS concentration, which is similar to the product Ka times HATS to the power of a half. That is the same as a square root, if you remember. Well, now we are in an aqueous solution. And now we need another trick. The concentration of HATS in the equilibrium. In the equilibrium, how much of that is remaining in the equilibrium? A part of it reacted to form ATS minus, and most of it stays as HATS when it is a weak acid, or minimum an important part stays as HATS. So we look to the concentration of HATS in the equilibrium. So the HATS concentration in the equilibrium is important. That is what we need here. The current concentration when it's already reacted. This is the concentration we had at the beginning, HATS apostrophe minus the amount which is already transformed into ATS minus. This is the concentration at the beginning, start or at beginning. This is the concentration initially we had, H at apostrophe. And now we are interested in the concentration after the reaction. Partially, H minus is built. So the concentration of the current at HS is the initial one minus the concentration of the H minus, which is already built. It's clear. Huh? If not, please ask. So that is the current concentration. In the solution or in the aqueous the current concentration is the start concentration minus the H minus, which is already built. The rest has to be quiet, and you please more loud. I do not hear very good. Acetic acid, yeah. The formula is that one. Acetic acid. CH3COOH. And we just call it now HS. It has one proton, which can be spent, this one, forming H minus, that's H minus. And that's HS. And what is the question now? I don't understand. It has we have two oxygen, but we don't care about it. We just care about the proton. Here you see the COOH, but what's relevant for the acid is this proton. Only the proton is relevant for the acidic current. We have two protons in it, two oxygen in it, and one proton here. Okay, you are with me up to now in the calculations. So now what we had here, we said H3O plus concentration is the square root of Ka times the concentration, the current one of HS. Yeah, that is what we said. This is same to say it is Ka to the power of a half times the concentration of HS to the power of a half. That's the same. And now we say HS is current starting minus that. And now we say we have, if Ka is very low, we have a weak acid. We have a weak acid. That means Ka is very low. So that means now the concentration of H3O plus is small compared to the concentration of the initial HS. is quite small compared to the H@ apostrophe at the start. And this is similar to H@. We say now that is similar to the initial start or to the current concentration. Because it is a very low Ka, not much of it is already transferred to Ats minus, not many of them. There is music. I don't like the music here. So now we are prepared. So we have these one. So again, H3O plus concentration is Ka a half to the power of a half times H@ current concentration to the power of a half. What does it mean for the pH? pH is the negative log of Ka when we transfer this one mathematically now to the negative log. The negative log to the power of 10, to the base of 10, of this equation, Ka to the power of a half times the concentration of H@ to the power of a half. What is it mathematically? And you transform it into another form. It is the negative log of Ka minus the log of the concentration of H@ over 2. It's mathematics. And this is pKa minus log of the concentration H@ half. That's true for a weak acid. So it's a little bit difficult to do it by calculation. For a weak acid, the formula is the pH is the pKa minus the log of the concentration of the acid over 2. So we know for the acetic acid, the pKa is, we already had it, 4.74. Now, as an example, let's say the concentration of the acetic acid is 0.01 mole over liter. Transforming it, it is similar to 10 to the power of minus 2 mole over liter. And now we have to calculate the pH of this solution of acetic acid with 10 to the power of minus 2 mole per liter in water. We need the formula. The pH of this solution is, the pKa is 4.74 minus the log of the concentration of 10 to the power of minus 2 over 2. What is the negative? What is the negative, or what is the log of that? Minus 2 minus minus 2 is plus 2. So it is 4.74 plus 2 half. That is 6.74 half. And this is 3.38. Compared, or 7. If you compare it with the acetic acid, the same concentration, when we have 10 to the power of minus 2 of the strong acid, HX, what was the pH of that? 2. Now we have 3.37. What is more acidic? Of course, a lower pH is higher acidity. And it is always a factor of 10 because it's a logarithmic scale, meaning the pH of 2 compared to the pH of 3 means 10 times more H plus ions when we have 2 instead of 3. No? So already 10 times more. One pH step is 10 times more or less in the H plus ions. So in general, and that's the last for today, for weak acid, the pH is pKa minus log of the concentration HA over 2. Please, this might be a formula to remember for weak acids. It's the same for weak alkali, then we calculate the pOH. For strong alkali, it's easy. pOH is the concentration of the alkali, similar to the strong acid. For a weak alkali, it's similar to that, but then not pH, pOH, pKb, no, for the base, minus the log of the alkali over 2. Okay, so I think a lot of things today are discussed. Thank you very much. We meet again next Wednesday.